All right, we're going to talk about work, energy, and power for a little while, and hopefully this will help you with the energy unit. Ignore the chapters. Those are on there from my traditional school where I teach. Let's say work and energy. Work and energy. Energy is very difficult to define. Actually, physicists have a hard time defining energy because there's so many different kinds and it manifests itself in so many different ways. And so for me, it's easier to define work and energy sort of together. Work is when an action that changes energy and we'll have an equation for it in a few minutes and that will kind of clarify some stuff. And energy is the ability to do work. So if you do work, the amount of energy that you have or the amount of energy of the thing that you're doing work on changes. And if you have energy, then you have the ability to do work. So it's kind of a circular definition. The units of energy and work are both a joule. And it's important to know what's hidden in a joule. 1 joule is a Newton meter. You don't have to put the dot there, but it's not newtons per meter. It's Newton meter. So a joule is a Newton meter. The equation for work equals force times distance times the cosine of the angle in between the force and the distance. Much of the time, the force and the distance will be in the same direction. The angle will be 0 and cosine of 0 is 1. So in most of your problems, the cosine of theta just comes out to be 1 and work is shortened to force times distance. So, well, and that's what this says. What happens when the force and the displacement are in the same direction? So if I have a box and I push on that box with a certain force and I push on it through a distance d and the displacement and the force are in the same direction, well, that means theta is 0 and the cosine of 0 is equal to 1 and work is just force times distance. If they're in opposite directions, like let's say I have pushed this box and it's moving in this direction with some velocity, but there's a frictional force acting in this direction and the box continues to move a distance d. So the displacement is in this direction. Okay, so the frictional force and the displacement are in opposite directions. Theta is then 180, and the cosine of 180 is -1. So when the force and the displacement are in opposite directions, you do negative work. So it'd be force times distance times the cosine of 180, which would be negative force times distance. So the work would just be negative force times distance. Negative showing that they're in opposite directions and you do negative work. What about when they're perpendicular? Well, if the normal force is acting in this direction, but if this person's pushing this box in this direction, the normal force does no work because theta is 90 and the cosine of 90 degrees is 0. So work equals force times distance times 0 and work equals 0. If the force and the displacement are in opposite directions, that force does no work. Now, he's pushing with a force to the right, and the force that he would be pushing with would do work. One example that comes up a lot is, let's say here's the Earth, and here's the Moon, and there's a gravitational force, in between them, the gravitational force. And the question will be, how much work does the gravitational force do on the moon? Well, you know that the moon's velocity is perpendicular to that force. Let's pretend that it goes in a circular path. It doesn't exactly. But if it goes in a circular path, then at every point of that circle, the force would be perpendicular to the velocity. And since the force would be perpendicular to the movement, to the displacement, the gravitational force does no work on the moon. If you lift an object using a force of 100 newtons through a distance of 3 meters, how much work have you done? Well, work equals FD cosine theta, and in this case, cosine theta is going to be 1 because you're lifting an object through a distance of 3 meters. You are using an upward force, so they're in the same direction. So it's going to be your force, 100 newtons, times your distance, 3 meters, which would be 300 joules. If you pull an object a horizontal distance of 10 meters using a 50 Newton force with a rope that makes a 30-degree angle with a horizontal, what work have you done? Okay, so here's my box. I'm pulling it with a rope that makes a 30-degree angle with the horizontal. I'm exerting a 50 Newton force, and I'm moving that box through some distance, 10 meters. So work equals FD cosine theta. It's going to be my force, 50 newtons, times the distance, 10 meters, times the cosine of 30 degrees, and the cosine of 30 degrees is 0.866. Did not get my calculator ready, so give me just a second. It's on my phone. I have to get unlocked. Sorry. Okay, so 0.866 times 10 times 50 gives me a total force of 433 joules. How much work does a waiter do on a plate of food that's on a tray that he's carrying across the room? This is that, here's our waiter, and here's his tray of food. He is pushing upward, but he is moving to the right. And so his upward force on that food is doing no work. There is a frictional force, a static frictional force, that is moving the block in the direction of the motion. And so the static friction force is doing work, but the waiter is not doing any work on the plate of food because he is exerting a force upward and moving it through a distance that is to the right. And since the angle is 90 degrees, there is no work done. Kinetic energy is the energy something has because it's moving. So you can say it's the energy of motion. The equation, kinetic energy, and some books just say K. I am in the habit of saying KE. Kinetic energy is 1/2 mv squared. 1/2 times the mass times the square of the velocity. An object with a mass of 20 kilograms moving with a speed of 10 meters per second. The kinetic energy, let's write that formula even if we just did, because that's what you're supposed to do, equals 1/2, and the mass is 20, and the velocity is 10, and that's squared. 10 squared is 100. 100 times 20 is 2,000. 100 times 2 is 2,000, is 200, so 100 times 20 would be 2,000, and half of that would be 1,000. And so the kinetic energy would be 1,000 joules. Did I do that math right? 100 times 20 is 100 times 2 would be 200, times 20 would be 2,000, and half of that is 1,000. Okay. Oh, that would have been so much easier if I had said a half of 20 is 10, and 10 times 100 is 1,000. Sorry. The work energy theorem says that the net work done is equal to the change in kinetic energy of an object. See, more than one force can be doing work at once. If I lift an object, I'm doing work, but gravity is also doing work. If I am exerting an upward force on this thing, let's say applied, but there's also a gravitational force. So the net work done, so that would be the work done by the net force, is equal to the change in kinetic energy. I'm going to put an E on that. Okay. So if the net work is 0, then there's no change in kinetic energy. So if I lift with the weight, if I am applying a force upward equal to the weight of the object, it's not accelerating, then there's no change in its kinetic energy. In throwing a baseball, you exert a force of 50 newtons through a distance of 0.6 meters. What kinetic energy will the ball have after you release it? Well, here's our kinetic energy formula, but we don't know that stuff. All we know is a force and a distance. Well, the work is force times distance. They're in the same direction, so we can shorten it to be FD equals 50 newtons times 0.6 meters, and that's equal to 30 joules. And if that's the work done, then that is equal to the change in kinetic energy. It started with 0 kinetic energy, and so it ends up with 30 joules of kinetic energy. If the mass of the ball is 0.1 kilograms, how fast is it moving? Well, now we can use the kinetic energy formula. So if kinetic energy is 1/2 mv squared, then the velocity is equal to the square root of 2 times the kinetic energy over the mass. You'll use this formula in the conservation of energy lab to find velocity, by the way. And that's equal to 2 times 30, that kinetic energy from up here, divided by the mass, which is 0.1. So 2 times 30 is 60, divided by 0.1 is 600. So the square root of 600 again. Let me grab my calculator, which is my phone. So it takes you to, there we go, it's open. So let me check that math again. 2 times 30 equals, divided by 0.1 equals 600, and the square root of 600 is about 24.5 meters per second. Power is the rate of doing work, how fast work is being done, or how fast energy is being changed. It has units of watts, and 1 watt equals 1 joule per second. It's how fast work is being done, or how fast energy is being changed. Power is equal to work divided by time. But remember, work is force times distance, and so power can be force times distance over time. And sometimes, you'll be given a force and a distance and a time, and you'll have to calculate the work first. But I want you to notice what we've got here. See this little bit right there? Distance over time. Well, that's a velocity. So that is equal to force times velocity. And that's a handy-dandy little formula to be aware of. You lift a 10 kilogram object a distance of 2 meters in 5 seconds. What was the power used? Well, power is work divided by time. We were not given work. So work is force times distance and then over time makes it power. And we're not given a force. We're given a 10 kilogram object. So what force do you have to use to lift a 10 kilogram object? So typically we're talking about lifting with a constant velocity, and so you would be lifting with its weight. And so the force is going to be the weight of the object, which is mg. Okay, I use 10 for g when I'm doing things like this, just because it's easy. And if you don't like it, that's okay. You can't do that on a test or a lab really, but it's handy dandy when I'm doing demonstrations. So the mass is 10 kilograms, and gravitational acceleration is about 10 meters per second squared. So that gives me a force of about 100 newtons. And now I'm going to plug it into the formula. 100 newtons times 2 meters in 5 seconds. So 5 goes into 120 times. 20 times 2 is 40 watts. There are several types of stored energy. Chemical energy, when you put gas in your car, you put it in there because there's stored energy in that gasoline. And when your engine burns it, then the bonds between the chemicals, the energy stored in those bonds is released. There's elastic energy. If you stretch a rubber band and you let it go, it'll go back into its original shape. So you store energy in it when you stretch it, and that energy is manifested when it pulls itself back into its original shape. And there's gravitational potential energy, which is the one that we're going to be talking about most. And I abbreviate PE. There are courses that abbreviate it as U. And some teachers are really picky and want GPE because there are other kinds of potential energy. But I'm just going to use PE for gravitational potential energy. And potential energy, gravitational potential energy, is mgh, mass times gravitational acceleration, which again, when I work out demonstration problems, I'm going to use 10 times, and it's actually a change in height. That delta, I hope you're familiar with, that's the Greek letter delta. And when we use it in science, it means change in. So mass times gravitational acceleration times some change in height. Let's see. Oops, the equation already, it's there. A 10 kilogram object is lifted from the floor a distance of 3 meters. How much potential energy does it have? Well, potential energy equals mgh, and that equals the mass, 10 kilograms, times gravitational acceleration, which I use 10 meters per second squared. And the change in height, I lifted it from a 0 point up to 3 meters, so the difference in height is 3 meters. 10 times 10 is 100 times 3 is 300 joules. Yeah, checking my math. So 300 joules of energy. Total mechanical energy is the sum of kinetic and potential energy. And so if I have an airplane and it is flying way above the ground, oh, that's supposed to be a tree. It's got a height, it's got a mass, it's got a velocity, and so the total mechanical energy would be the kinetic energy 1/2 mv squared plus the potential energy mgh. And that is the end of our session. I will talk about conservation of energy in my next lesson.